Okay, hello everyone. We are going to finish up 3.7 today, and that will be the end of the chapter 3. And then we're going to move back into our previous textbook, the online textbook that you had from the beginning of the year. Okay, so in this section, what we're going to talk about is the graphical behavior of intercepts and vertical asymptotes, because what we want to do is be able to take the graph and sketch the graph without really just having some information and looking at this. So you can find these notes in the textbook, and I have that link on the assignment page for this week, for this particular assignment as well. So the graphical behavior of rational functions at the vertical asymptote, so what we're talking about, right, just like we looked at before, we kind of think of it as end behavior, but in the sections on either side of the asymptote, the vertical asymptote. So, right, if we have one asymptote, and what that looks like, so we have it broken out like this, and so on. So we're just going to go through an example. Feel free to write this definition down in your own words to help you with that. All right, so when we're going to sketch the graph of a rational function, what we want to do is identify these particular points. So I want to find any horizontal asymptotes. So remember the horizontal asymptotes. The horizontal asymptotes are where we had the conditions, and so I need to look at the power of the numerator compared to the power of the denominator. So I see in the numerator I have x times x, which is x squared, and then in the denominator, this is squared. So I have x squared times another x, that's x to the third. So the degree in the numerator is 2, right? And the degree in the denominator is 3. So I know my horizontal asymptote is just y equals 0. And so you may want to go ahead and just draw that in, right? And since it's on the x-axis, I'm going to go ahead and just, right, dash this in as my horizontal asymptote. So that's y equals 0. Okay, next we'll find the vertical asymptotes. So remember, vertical asymptotes, that's where the polynomial in the denominator is equal to 0. So I would take x plus 1 equals 0 and x minus 2 equals 0. So I know that we cannot have a 0 in the denominator, so x cannot be negative 1 and x cannot be positive 2. So again, those are my vertical asymptotes. So at negative 1, I can draw in my vertical asymptote. This is x equals negative 1. And then at 2, I have another vertical asymptote. So I know x equals 2 is my other, right? That's the other place that x cannot be equal to, the denominator. That would make the denominator equal to 0. So we want to be careful with that. Okay, so a couple other points that we want to find. The y-intercept. So remember, the y-intercept is, I'm just going to plug a 0 in for x. So I have 0 plus 2. I'm just going to do this on a separate sheet of paper. So 0 plus 2 times 0 minus 3 divided by 0 plus 1 squared, 0 minus 2. All right, so simplifying, I get negative 6 in the numerator and negative 2 in the denominator. So that is 3. So I know my y-intercept is 0, 3. Okay, now let's find our x-intercepts. So remember, the x-intercepts happen when the numerator is equal to 0. And so we want to take the polynomial that's in the numerator, and this one's already factored out, so it works out really nicely. So x plus 2 equals 0, and x minus 3 equals 0. So when x is negative 2, or when x is 3, that's where you will have your x-intercept. So I have the x-intercepts at the point negative 2, 0, and 3, 0. Okay, So now that I have all these points, I'm going to take my graph, right? I'm going to plug the values in. I'm just going to sketch it. So I'm just drawing in the different points and then going from there. So now, let's see. This would be, so we already put in our asymptotes. We have a Y-intercept at 3. So I know the right? And then I know that the X-intercepts are at -2, 0, and 3, 0. And there are essentially 3 parts to this graph, right? So now we can just grab some extra points and sketch this in if we wanted to. Right? So I know I have I could look at the end behavior as X gets larger, what happens to this whole graph. And so that's where you would just find extra points, and you can use your calculator for that. I'm just going to go ahead and draw this in so that you can see what this kind of looks like. So this kind of goes this way. And then again, you can use your, this is going to go up this way. We would want to grab some extra points. Now, the nice thing is that you will always have your calculator or technology to help you through this. Okay. So maybe it looks something like that. All right. Let's move on. So if you're writing a function, so let's say I give you the graph and you're writing the equation of this function, right? So now we're going to use this information. It's kind of reverse of what we just did. And so we know that there are intercepts, so our X-intercepts are at, I know I have -2, 0, and I have 3, 0. So remember what caused the X-intercepts, that's where your factors in the numerator were equal to 0. So I know for this function in the numerator, and so I'm just going to write it down here, f of x is equal to, what I know so far is x, if -2 is a 0, this must have been x plus 2, and 3 is a 0, then that's x minus 3. I know those are in the numerator. And then I can look and see where there is so the vertical asymptotes are here. This is remember the vertical asymptotes are where we can't, that would make the denominator 0, and we don't want those. So I know I have x plus 1 in the denominator because the asymptote goes through -1. And then I also have x minus 2 in the denominator because I have, that would also make it 0. Okay, and so when I look at this graph now, I can see that, right, this appears to be a parabola, so I know that the y-intercept here is -2, and so I can plug that in to calculate this. By the way, this part right here is right, it's indicating like a parabola, which is a squared function. So we would want to make that squared here at that x minus 2 asymptote, right? Okay, so then but we know that there's some other value in front of all of this. So what we want to do is we want to plug in our y-intercept, which is 0, -2. So I have -2 equals a times, well, 0 plus 2 is 2, 0 minus 3, so that's -6, 0 plus 1, but this is 2 squared, negative 2 squared, so this is going to be 4 times 1, which is 4. Okay, so now solve this for A. This reduces to 3/2, right? And then I multiply by the reciprocal, and it's negative. So I get that A is equal to 4/3. Okay, so now you can put that in your function. F of x is equal to 4 times x plus 2 times x minus 3 over 3 times x plus 1 x minus 2 squared. And remember, that's just, right, that's a possible equation for this. We could do some other stuff that would give the same type of equation, but this is one of them. Okay, so I hope that makes sense, right? We're just reversing what we did before. And so now the last thing I want to talk about is what are called oblique or slant asymptotes. So remember, when we have that situation where we're looking at the degree of the polynomials, so if I have, if I called the degree of p of x, if I said that was m, and then the degree of, so this was last week, q of x was n, right? So if m is greater than n, meaning the power in the numerator is greater than n, and it's, right, then we could have, we did not have a horizontal asymptote. So you want to kind of refer back to the notes from the first or last week when we were talking about the asymptotes, the horizontal asymptotes. Okay, so we want to look at the slant asymptotes. The condition for this is that you would have, so this condition before, when we get this, when the degree of the numerator is greater than the denominator, there could be a oblique asymptote. All right, so what we do is now we're going to bring back that synthetic division. It says long division. I didn't go over that because I found that in the years, a lot of students don't know long division anymore. So we weren't going to spend time going over that, especially with the distance stuff. Okay, so what we're going to do is we're going to set this up. We're going to set up our synthetic division. So I know that if I'm going to divide 3x squared plus 2 by x minus 5. So I put in a 5, and then 3x squared. So remember, when you write this, I have to account for every power. So 3x squared plus 0x plus 2. So I have to have a placeholder for the x term. Drop the first term down, multiply, add, multiply. So 15 times 5. Ooh, I should know that. 75. Right? And then you add and you get 79. Okay, so you're always going to get a remainder, right? We don't care about this term. This is what we care about here. So I have 3x plus 15 and with a remainder. Okay, oh, it's not 79, 77. Okay, I can add 77 would be my remainder. Okay, so this equation here, so remember we had x squared, we factored out an x, so your oblique asymptote is the equation 3x plus 15. And then you would graph it just like you would graph the line of 3x plus 15. Okay, so let's try another one. So on this one, I'm going to, again, set up my synthetic division. So I have, since I'm dividing by x plus 1, this is going to be negative 1. So my first coefficient is negative 1. I have all my terms this time, 2 and 1. Drop the first term, multiply, add, multiply, and then, right, this I don't care about. That's my remainder. So now I have negative x plus 3 is my slant asymptote. Okay, I hope that makes sense. Give it a try. There's just a couple of problems that I have you do with the slant asymptote. The key is to remember you're just factoring out 1 power of x. Okay, have a great day, everyone.